Alleviating the long-tail problem in conversational recommender systems. This paper introduces a novel framework to address the long-tail recommendation problem in conversational recommender system by simulating a balanced conversational recommender system dataset using publicity collected item attributes. The presenter is Xiaoli Wang from Guoling School of Artificial Intelligence. Okay, please go ahead.
Okay, thank you. Hello, everyone. I'm Xiaoli Wang, a PhD student from Renmin University of China. I will introduce our paper collaborated with Huawei Pusong Lab, Alleviating the long-tail problem in conversational recommender systems. First, I will give you some background information about conversational recommender systems. It aims to provide the recommendation service to users through natural language conversations. Usually, it consists of two modules, namely the recommendation module to predict suitable items and the conversation module to generate appropriate responses. Look at this example. The system first asks the user for his preferences about the music genre and the singer, and then recommend a song accordingly. Compared to traditional recommender systems, CRS can proactively elicit user preferences through online conversations, which is more accurate. Then let's look at PRM-based CRS. Usually, it first use an encoder like BERT to encode the conversation context. Then, for the recommendation task, it takes the representation of the CRS token as the user representation for prediction. While for the conversation task, it uses a decoder like Dialog-GPT to generate the response. As a representative work, UniCRS proposes to unify these two tasks through knowledge-enhanced prompt learning with Dialog-GPT. And in this paper, we aim to solve the long-tail problem in CRS. As we can see in the left figure, many items are rarely mentioned in the dataset, and the CRS trained on them will be affected by the exposure bias, as shown in the right figure. Both models perform so badly on the examples whose labels are long-tail items. And for the long-tail problem, existing work mainly adopts resampling, instance weighting, and regularization. However, they cannot effectively solve the fundamental problem of context understanding and preference learning in CRS. So to address this issue, we propose ROT CRS, which is a general framework for PRM-based CRS. The key idea is to simulate a balanced CRS dataset and design training strategies based on the simulated data for context understanding and preference learning for long-tail items. First, let's look at dataset simulation. It has 4 steps. The first step is to collect item attributes from item descriptions and reviews. We use TF-IDF to select top keywords from them as item attributes. Then to build conversation threads, we select an attribute as the starting point, and then randomly add new attributes into the thread one by one until the target item can be located. Finally, we simulate procedural conversations based on these threads. We take a simple but controllable template-based approach. We extract high-frequency sentences from reviews as templates, and then fill the attributes and items from threads into them to form conversations. Such an approach allows us to easily control the frequency of items. And with the balanced CRS dataset, we design 2 pre-training tasks. The first task, domain adaptive masked prediction, aims to inject attribute information into PRM. It randomly masks some item and attribute tokens and require PRMs to predict. The second task, contrastive context alignment, aims to enhance the contextual understanding of items through contrastive learning. We sample conversations with the same target item as positive examples and use in-batch negatives. After pre-training, we further use human-annotated datasets for fine-tuning. Since the rare datasets are long-tail, we use the retrieval-augmented learning strategy. For recommendation, we first generate retrieval-enhanced user representation. It takes the CRS token as the user representation, retrieve top K most similar user representation from simulated data, and aggregate them through cross-attention. Then we perform fine-tuning with label smoothness on long-tail items. Standard cross-entropy loss usually uses hard label, which will lead to exposure bias with long-term label distributions. To solve this, we use the teacher model trained on the simulated data to produce soft labels. We also add the contrastive context alignment loss to enhance the connection between conversations and items. While for response generation, first we follow the recommendation task to enhance the representation of each token through retrieval and cross-attention. These enhanced token representations will be used as soft prompts. Then we generate the response. Considering that long-tail items are hard to generate, we replace items in the response with a special token and only require the decoder to generate a template. Then we will fill recommended items into these slots as complete responses. Now let's move to the experiment part. We choose two CRS datasets, Redire and Inspired. They are both about movie recommendations, but with different sizes. Following previous work, for the recommendation task, we use record at K for evaluation, while for the conversation task, we use distinct for automatic evaluation, fluency and informativeness for human evaluation. As for long-tail problem, we can use coverage at K and tail coverage at K to measure the diversity of all the predicted items and long-tail items. The main results of the recommendation task are shown in the table. We can see that our method can improve existing PRM-based CRS and with a large margin. And the same goes for the conversation task. Compared with existing methods for the long-tail problem, our method is much better since we consider the intrinsic problem in the data. Then we perform ablation study. We can see that all components are useful, and removing any one will lead to drop in performance. We also perform hyperparameter analysis. To summarize, in this paper, we simulate and utilize the balanced CRS dataset to solve the long-tail problem. We also develop a Turkish CRS lab for CRS-related research. You can try it to carry out your experiments. Thank you for your time and listening.
Thank you very much for your presentation. This is still an explored topic on conversation recommender systems. So it's time for questions.
Hi, I'm here. Zhenhua Dong from Huawei Nuance Arc Lab. So it's a very good presentation. I have a quick question. Did you analyze the teacher model? It's very important. How to guarantee the unbiased of your teacher model? Yeah.
Yeah, that's a good question. I think you can contact the first and second author for further details. Sorry.
Okay, so what's kind of your teacher model? Which model you use?
Yeah, as I know, we use a CRS model named KBRD, maybe you know, and we train it on the simulated data, so it can produce a soft label especially for the long-tailed item, to provide some supervision signals for them to help the main model or the student model to better predict long-tail items.
Okay, thank you.
Okay, thank you.
There is another question over there, please.
Thank you for the talk. I have a question about the matching. So you mentioned that the model generates a template and then it matches it with an item. How is that done?
As I mentioned before, since the long-tailed items are hard to learn and hard for the decoder to predict, so we replace the items in the response labels to a special token, the item token. You can understand it as a special ID like CRS or PAD or others. So we only train the decoder to predict response templates with these special tokens. So it does not need to learn to predict these long-tail items, which is very hard for the decoder, and we can just fill the predict items from the recommender module into these predicted response templates.
How is that feeling done? That's my question.
Okay. To fill that, you just need to identify the slots and fill them. Yeah, fill the items into these slots. Maybe a very common action in task-oriented dialogue systems. So can you understand that?
Or maybe I try to grab you after the talk. Thank you.
Okay, thank you.
Okay, thanks. I have a question about the user evaluation, human evaluation you carried out. Can you provide some additional details about the number of participants, the task that they asked to do?
Sorry, what's the...
In experimental evaluation, there is a user study, right? With real users.
Sorry, I don't understand your problem. Maybe you can...
Can you go to the slide of experimental evaluation?
Which slide you mean?
Your experimental evaluation is composed of a part related to a user study, a human evaluation, right? No? Sorry, I didn't.
Sorry, my English is not.
Okay, don't worry. Any other question? Okay, thank you very much.